Hi everybody, and welcome to my session on rock-solid device connectivity. My name is Kai Hudalla. I work for Bosch, and I'm currently also being paid there to work as a committer on the Eclipse Hono project, which is being used at our company for implementing IoT applications using Eclipse Hono as a device connectivity layer. So what I want to do today is share with you some of the experiences and the insights that we gained throughout doing these projects, these real-world IoT projects with customers, where we learned quite oftenly that some of the problems that prevented the application or the solution from actually working as intended was to be found at the very lowest layer of device connectivity. And so what I want to do today is share with you some best practices and recommendations regarding how to actually connect your devices to any kind of backend application, really, in order to get better connectivity and have a better experience with your application. So in order to do so, let's take a look at a very simple application. In this case, we want to connect a smoke detector to a smart home application, and the smoke detector in normal operation would simply report the current temperature from time to time, let's say every 60 seconds or whatnot. And the more important thing, however, is when it detects smoke, it needs to issue an alarm that it has detected smoke and that maybe a fire alarm is being set off. So why am I showing this to you? Even this very simple setup also constitutes a distributed application, a distributed system. And we all know what the first rule of distributed systems is. It is don't distribute unless you have a very good reason to do so. And that is because there are several impediments involved when you distribute a system. And several of them, in particular 8, have been identified by Peter Deutsch and James Gosling and are very well known as the 8 fallacies of distributed computing. I do not want to go through each of these in detail, but it is worth mentioning that many, if not most of them, are in particular related to the network being involved when communicating between two processes. And there are certain misunderstandings or misassumptions that often lead to systems not really working as they should. There is also another cue to that. In particular, message ordering in a message-oriented system is of some importance in several situations. However, maintaining message order is one of the harder problems actually to be solved. And I also will not get into details about message ordering. I just wanted to point out that I'm not the only one who thinks so. So if we take a look at how such an application might be deployed in real time, you would probably have an STM32 microcontroller in the smoke detector, which is running some firmware and which is responsible for implementing the connectivity to the backend application. And your backend application in this case might be deployed in a public cloud environment in a Kubernetes cluster. So in reality, your smoke detector will talk to a load balancer, and the load balancer will distribute the traffic to an instance of your smart home application. So the first question that arises is, how do you actually transmit the data? Meaning the real temperature values or the alarm itself, how do you convey that to the backend application? And as with every application that communicates over public internet infrastructure, you are pretty much restrained by the IP protocol and the TCP or UDP session protocols running on top of it. And this whole stack is usually provided by the operating system or the firmware that you are running on your device. So there is not much choice you have there. You can use TCP or UDP, that's up to you. But then on top of that, you're pretty much on your own, and you have to use an application layer protocol, and that is your choice. So what I try to recommend to you is to not invent your own protocol there, meaning do not start writing raw TCP streams with the temperature value and say this will always be 5 bytes, and after 5 bytes the receiver can interpret the data. Instead, I want to recommend to use an existing application layer protocol. And there are several, of course. Many of you probably know all of them or some of them. In particular, MQTT has been dubbed as the IoT protocol throughout the last years. IBM has done a terrific job of doing that. And this table is supposed to give an overview of what protocols are there, what are their pros and cons, and they are ordered by preference. That is actually my personal preference, but I can also put some rationale behind it. In particular, what I would discourage you from doing these days is using MQTT 3.1.1 in anything else, but very, very simple telemetry only use cases. The main reason for that is that it does not provide negative acknowledgements, meaning a sender of a message never knows if a message could not be processed for some reason. And also it does not provide any means of including any metadata in messages. So you cannot include any additional information like what is the payload semantic, like you could in any other protocol by means of indicating a payload type, a content type or something. There is simply no such thing in MQTT 3.1.1. The other protocols do allow for that. They also allow for authentication of the peer, of course. Most of them run over TCP. Only one of them is defined to be run over UDP, and that is CoAP. And CoAP in particular is very specific in that it has been explicitly designed for constrained devices. In fact, CoAP stands for Constrained Application Protocol. And constrained meaning constrained with regard to processor, memory, power supply, stuff like that. So it is intended to use very, very small messages, often only several bytes or several dozens of bytes, while still providing some level of high-level request response semantics. In fact, it has been dubbed as binary HTTP. So it has the same verbs like get, post, put, stuff like that. So an application developer who is familiar with implementing an HTTP-based client can usually easily also implement a CoAP-based client. Then MQTT 5 is the newer version of MQTT 3 and actually added most of the features that have been lacking in MQTT 3 to make it on par with AMQP 1.0, which from my point of view is still the most preferred protocol, in particular because it has excellent support for flow control. So in some applications that is very helpful and important, but otherwise you can choose whichever protocol is to your liking or you're most familiar with. HTTP, of course, has the very big advantage of being very ubiquitous, meaning there are many implementations available and most people have already experienced using that protocol. On the other hand, it is very verbose, meaning all the data included in a request is usually text encoded and therefore requires a lot of overhead. But anyway, so this is just an overview. So the next question then is how do we keep confidentiality when we transmit the data? And the obvious choice here, of course, is using a standard layer being added on top of TCP and below the application layer. And that is usually called TLS, Transport Layer Security. There's also a UDP-based variant called Datagram TLS, that's the DTLS. And if there are no other specific requirements regarding payload encryption or something like that, this is what I would always recommend you to do. Always use TLS or DTLS using one of the existing libraries or operating system functionalities that are available. Do not do this yourself. And this is usually true for everything around security. Do not start implementing your own security mechanism or layer. You will usually fail with it, or at least it will only work in certain circumstances. It will not be resistant to reasonable attackers. On the other hand, everything that is done around TLS these days is being reviewed by real experts, and they really do an excellent job in doing so. In order to better understand what TLS actually does, it's worth taking a look at the handshake protocol. So for a TLS version 1.2 handshake, a fresh handshake, there are two round trips involved, meaning a device sends some messages to the backend answers, and the device sends another bunch of messages, and the backend again answers. And it's not so important to understand each of these messages. So the point is, there are two round trips usually involved in a fresh handshake, and the messages being exchanged, the size of those depend on the negotiated cipher suite. The cipher suite is the set of parameters that are agreed upon by the two parties in order to come to an encryption key that is being used to encrypt the message from after the handshake has been established. And you can make some wise choices or some wise configuration in order to improve or decrease the size of these messages being exchanged. I'll come back to that later in a minute. As opposed to that, you can also use an abbreviated handshake, which is called session resumption. And the main advantage of that is that it's only 1.5 round trips, but that is not the biggest advantage. The biggest advantage is that the messages being exchanged are much, much shorter and smaller than in the full handshake example. That is mainly because there is no need to exchange large certificates and public keys and whatnot. So in order to provide you with an overview, this table is divided in 3 columns, which identify the different authentication mechanisms that can be used in TLS, or which are the most prominent or popular ones at least. One of the oldest ones is RSA. That is what you usually use with existing private public key pairs that you can get from VeriSign or whoever. In the middle column, that is ECDSA. EC stands for elliptic curve, and DSA is a digital signature algorithm architecture. This is a newer version doing basically the same as RSA, but with much less data involved. So what you can see here is that the certificates being issued are at most half the size of RSA certificates, and provide for, therefore require much less data being transferred in a TLS handshake. The typical key length you see there as well. You see example TLS 1.2 suites that are recommended by government authorities in Germany at least to be used and are considered secure at least until 2027. And what you also see is the impact that the different types of authentication mechanisms have on the full handshake and the abbreviated handshake. So with an RSA-based handshake, you get to 4 to 7 kilobytes, mostly depending on the number of certificates in a certificate chain that your server or client needs to send to the peer in order to validate the peer's certificate. With ECDSA, that is, as you would expect, roughly half the size. And in the rightmost column, PSK stands for pre-shared key. That does not involve any private public key infrastructure, but instead is simply based on a shared password, if you will, that both the client and the server share and are being pre-configured with. And they use the knowledge of this shared secret to authenticate to each other. And with this, of course, the handshake is the smallest ones. So why am I telling you this? Based on the hardware that your device is built upon, you might want to consider one or the other. If you have very decent hardware with a powerful processor, then it's not really much concern. But if you want to use the cheapest and smallest hardware that you can get your hands on, for example, a Cortex M0 class device, then it might be worth considering using only PSK instead of the certificate-based cipher suites. So some best practices when dealing with this. As I said before, do not implement your own custom security layer. You will probably mess it up. TLS 1.3 has been released, I guess, I'm not really sure, a year ago or something. The main advantage over TLS 1.2 is that it has a shorter handshake and that it has ruled out a big set of cipher suites that had been usable with TLS 1.2, but which had been considered unsecure already. So whenever possible, use TLS 1.3 if your device's operating system stack or TLS library supports it and your backend also supports it. And never use anything prior TLS 1.2. That is simply because anything prior to TLS 1.2 is known to be vulnerable to several attacks and therefore should never be used again. Then another thing is that you should configure an appropriate set of cipher suites. And the point here is that during the TLS handshake, the client usually tells the server, well, I can take part in a TLS handshake using this and this and this cipher suite. And the shorter that list, the more likely it is that the session will be established using your preferred cipher suite. So you can make sure by setting a short list of, say, 2 cipher suites that you get what you want, and that you can, and in this way you can influence the way that the session is being established and what type of properties are being used. So if you use a certificate-based cipher suite, then it usually makes sense to configure your client's trust store with the issuer certificate of your server's end certificate. That is important because, or that is helpful in order to allow the server to only send its end certificate instead of the whole certificate chain, which would be required to validate the server certificate. But if the client already has the issuer certificate and can tell the server about it, which it does in a TLS handshake, then it is sufficient to only receive the end certificate of the server, which reduces the data being exchanged again. Then, as you have seen, it seems to be a good idea to support session resumption if possible. For that to happen, you must make sure that your client or your device actually retains the session state, the TLS session state. So that might be a configuration that needs to be enabled or set in your TLS implementation on the client, but it's certainly worth doing. Then if you are transferring data that is very sensitive and for which you want to make sure that past transmissions of data will not be prone to a compromised key in the future, then you will probably want to use a Diffie-Hellman ephemeral exchange in your TLS cipher suite. So there are certain variants of them, of the cipher suites, and some of them include this DHE acronym, which stands for Diffie-Hellman ephemeral, and only if that is in the cipher suite name, you can usually assume that it provides for perfect forward secrecy, which is the property that I described before. With TLS 1.3, DHE is part of all accepted cipher suites, if I'm not mistaken. So with TLS 1.3, you do not really need to bother. Then, and the last point, however, is very important. If you are devising a new system, then make sure that you think about key and secret rotation as a requirement of your system. And that means make sure that from the very beginning, you have an idea, an understanding of how you actually want to provide the device with a new credential set or with a new client certificate, or how you want to rotate the shared secret if you use PSK. That might be by means of implementing the possibility of a firmware update on the device, a remote firmware update triggered by the device, for example, or even by means of somebody walks over to the device and puts in a USB key with a new secret. In any case, make sure that you think about this up front, because you will probably not be able to add it later. So now the last step is how to make this whole thing robust, meaning how can you make sure that a device always gets its connection and behaves appropriately when it fails to do so. The worst thing that can happen is that you end up with bricked devices, meaning that there is a device out in the field which is not able to connect to any of your services anymore. So that is what you usually want to prevent, because then you need to walk over or send somebody to do something with the device and update it manually. So based on the networking architecture, what a device usually needs to do in order to talk to the backend is establish 3 layers of connectivity. One at the TCP layer, one at the TLS layer, and then one at the application layer. And that is what has been depicted here. And the RTs means round trips. So if you add them up, then you end up with, I don't know, 4 to 9 round trips. And all of these connections need to be established before your device can actually send some reasonable data. So it makes sense to make sure that you do not need to do this too oftenly. And if you do that it has a good chance of actually work at the first attempt. So good practices include using DNS to resolve the backend host's IP address. The point of that is that if you are in a cloud environment, then the IP address of the load balancer, for example, might change from time to time. And in order to be able to connect reliably to the load balancer, it makes sense to resolve its logical name to the actual IP address using DNS. For the same reason, it also makes sense to not cache that data, that resolved data, endlessly, but for a short time only. And short means, 30 seconds or something like that, so that you can actually connect reliably to the current IP address of the load balancer. Then what you should also do is, if your client library or your application library supports it, register a handler, code handler that will be invoked once a connection establishment has finished. Independently of whether it was successful or unsuccessful, it is worth being notified about the outcome of the attempt to connect. Then the next one is use an aggressive connection timeout. And the point here is, by default, a TCP connection will probably time out after a minute or several minutes only, meaning if after 2 minutes the TCP connection is not established, then the code will fail with an exception. But in most cases, that doesn't really make sense. It either works basically instantaneously or it doesn't work at all, meaning an aggressive timeout might be something like, 2 seconds. If after 2 seconds it has not been established, it won't happen anymore. That is, at least that is my experience. If it doesn't work, then it usually means that in the backend, a component has been shut down or crashed or had been rescheduled to another computing node. So in this case, it makes more sense to try again, meaning after 2 seconds, if the connection is not there, simply stop the attempt and try to connect again. But do not do that directly after the first failed attempt, but try to implement a backup algorithm, maybe even an exponential backup, meaning after the first attempt, you wait 1 second. After the second, you wait 2 seconds. After the third, you wait 4 seconds and stuff like that, so that you do not overwhelm the other side, the peer, with your requests. When sending a message using your application layer protocol, then what often happens in library or in client libraries is that you have a local method that you can implement, that you can invoke to send a message. And then your client has an outbound message buffer to which it appends the message being sent and simply returns with a success for your invoking code. And then asynchronously in the background, the client tries to transfer the message to the server. And then depending on the outcome of the message, the transfer has been successful or not. It has been accepted, rejected, released, at least in the AMQP case. The problem with this is that, as you can see in the sequence diagram, the original send operation is now completely decoupled from the actual transfer. And so your application layer code does not really know if the transfer has succeeded or not. What you can do, at least in AMQP, and what you can also do in other libraries, is that you can register a disposition handler, meaning when you send the message or when you invoke the send message, you provide a pointer to a piece of code that you have created, which is then later on being notified about the outcome of the transfer. Thereby, you have a chance of reacting to the outcome of the transfer. And this makes your whole application much more robust, because you now can figure out whether sending the message, or in particular in our example, sending the fire alarm, has actually been successful, meaning that it can be reacted on. So again, the best practices for sending messages include what I just said: register a handler for the message outcome, and then also use an aggressive negative ACK timeout. Meaning, again, it doesn't make sense to wait too long for such a disposition update. In reality, it usually is a matter of milliseconds to transmit such a message. So if you do not get an acknowledgement after a second, you can basically assume that your message got lost, or a system has crashed, or a component has crashed. Then again, try again to send the message, but also again include a backup algorithm in your retrying. And I think with that, I'm at the end. I would like you to evaluate the session to provide some feedback. But apart from that, I think we're 5 minutes to the end, so we now have some time for questions. And I think there are some questions I see in the chat. So question one is there any drawback when one always uses perfect forward secrecy? I don't think that there is a real drawback. The only general drawback of perfect forward secrecy is that it involves usually calculating a session-based private key as part of the TLS handshake. So it incurs a little computing overhead, processing overhead. But that is only done during session TLS handshake time, meaning it is done once, and then as long as the session prevails, it can be used. So I would say no. In most real world scenarios, I would say there is no drawback. Question two, how safe is it to make TCP timeout less than standard? Can this be the reason of problems when working, for example, with slow gateways? I have to admit that I have no experience with slow gateways. My personal experience is that when you use public internet infrastructure, things usually work pretty quickly. I'm not really sure if I understand what you refer to with TCP timeout. I was referring to a timeout that the client starts when it tries to establish the connection, and if the connection has not been established during that time, you consider the attempt as failed and simply start a new one. So personally, I haven't seen any problems with that. The only problem that I have seen is that if you do not use an aggressive timeout, the devices are basically stalling, waiting endlessly for connections that will never get established. Anything else? Well, no more question. Okay. So then, thank you everybody for your attention. I hope it was worth your time and you learned a little detail which can help you make your IoT application more robust and more secure. Thank you. Bye.